Okay, just for refreshing what I covered, just briefly, that in the previous class we derived the nonlinear equation of the moving pendulum and we transferred through in MATLAB through the state space equations, and we transferred also the linear. We're going to simulate together to see differences and how we have to exert the code later, but now I'm going to show you here the MATLAB command for the control command in the block diagram. Okay. So let's go to MATLAB that I started in the previous class. Here we go. So I said this is the code that we started. Control pendulum stability problem. As we know, is internally is the marginal stable system, and this is the length of that, and this is the disturbance minus sine, right? Yes, and x double dot. So let me write here. This was for reference dd dot ddx x double dot disturbance, and this is g gravity, and we did it. And this is the exactly the right hand side of the equation, omega n square sine m1. Now we have to solve this, right? So you have to write always in MATLAB CLC. Look at here. If I say 1, 2, 3, 4, 5. Okay, 2, 3. CLC gonna clear your workspace. Okay, CLC, always do it. I'm gonna share it with you. Clear all. This is another command. It's gonna clear all the variables for the next run. It's good to do it. And close all. This command's gonna close all figures for the next run. Close all figures for the next run. Okay, always do this. Okay, this is good. I'm gonna name it, save it at the same folder. You have to, if you're not familiar with the MATLAB from my vibration class, you can do whatever you want. Say solver, control, I don't know, control, stability, moving pendulum. This is whatever you want, okay? This is the name. So now we have to go here. You have to say bracket time, total time, and the angle theta. This is the output of the system. Then ODE 45. You have different ODEs. Just go to the MATLAB help, say ODE. Okay, ODE 23, ODE 15, ODE 115 or 15S. You can go and find it that what kind of the differential or the different ordinary differential equation solver. I'm selecting ODE 45 and then at in MATLAB means go and call another M file. This is one M file, that's right, we created. So this is the MATLAB M file name that we saved from the previous class. Okay, go and call this. Okay, and again, these two must be in one folder. If they're in a different folder, it's gonna give you syntax error. Okay, and then you have to say time for which time interval you want to do that. I'm gonna say time bit from 0 and step off to 0.0 to 10 seconds. This is how we write intervals. See here, guys. If I run it here in MATLAB, I'm just do it one time, but when I go to control, real control, you're gonna see that. Here we go. You have this starting from, see, 0 and until to 10 seconds. Okay, here we go. This is how we write in MATLAB time. And then the initial condition. Okay, I'm gonna say, don't forget, we have two state variable. M1, I'm writing here, guys. M1, oh, what was that? Okay. M1, as we did, is for pendulum angle, and M2 was for what? You tell me from the previous class. Is for angular velocity. Okay? Velocity. Okay? We got it? That's why dm2 means angular acceleration. That's right. So that's why dm2 is angular, or theta double dot, angular acceleration that we did in mathematically. So I'm gonna say starting from 0 and 0. Okay, this is the initial condition I want to have. We can write like this, and then here we go, close it. Okay, now after this I'm gonna say figure 1. Okay, plot. Okay guys, look at here, all of you. Suppose I have a matrix, because you have to know this as a control engineer. 1, 3, 4, minus 10, 5, 6. This is just a vector, that's right, not matrix. Okay, can you see it? Now I say if give me first row and the fourth element, fourth column, it's gonna give you minus 10. As you see, it is minus 10. Here we go. See what I'm doing? If I say give me third element, gonna be 5. Okay, now if I generate a vector like this as 2, 3, 4, 5, 6 and 0, 4, 9, 9, minus 1, it's gonna be 2 by 1, 2, 3, 4, 5 what? Matrix. That's right. And non-square. If I say give me B, all the rows of the first column, this means all the rows, guys, all the rows. And the first column, you have to see 2 and 0 here. Okay, see 2 and 0. If I say give me third column, you're gonna see 4 and 9. Here we go, 4 and 9. Are you following me? It's clear, everybody? Yes? Yes, guys?
Yep.
Good.
Yes.
And if you say, I don't know, fifth, 6 and minus 1. Here we go. Now, if you change the places and say second row and all the columns, means this, guys. This is second row, all the columns, okay? This is how we write in MATLAB. It's gonna give us 0, 4, 9, 9, minus 1, as it is. See? So this is how we call the all columns of this differential equation solver. So it gives this theta, this t is total time, this time, okay, output. This theta is for angle. I'm writing here because I'm going to share with you. This theta is for theta, okay, all the thetas. But we have two rows, look at here. So I'm going to say plot time versus theta, all rows and first columns. This is for angle, that's right. So you have to multiply in radian. You have to multiply by 180 divided by pi. Now this is degree. Okay, I'm gonna say in blue. Here we go. Then I'm gonna say gridded. I'm gonna say X label. Put time in second. Okay, and the Y label. I'm gonna say put theta. I'm gonna write like this in degree. Okay, let me run it to see what we get. First of all, change folder. Here we go. See, this is the oscillation of the moving pendulum. This is angle of the pendulum. See that this breaks because of the base motion is what is moving. Okay, so bear with me. It means that this is, we have to increase to 30. Here we go. Here we go. This is how you have a transient phase and steady state phase of the oscillation of the pendulum. I have many lessons today. You have to bear with me. I want to just make sure that everything is right. There we go. See, it's moving like this. It's harmonic, okay? And this is like that, okay? Now, I promised you that I want to compare the nonlinear version of that with the linear version of that. Where is that? Oh, here we go. Okay. This is what we modeled, this line, original one, that we want to control it in this class. But we transferred by the Taylor's expansion to this version. That's right. We eliminated sine with theta and cosine removed. So what I'm gonna do, I'm gonna add another things here. Look at here, guys. Simple like that. Stop me, okay? Now we have 4 state variables. 4. Nothing changes except these, guys. Except these. Copy. Here we go. dm3 is m4 and dm4. These are new, that's right. And I'm commenting because I'm going to share with you. This is for non-linear pendulum we want to control at the end of semester. Okay, we're going to back to this at the end of semester. But this is a linearized pendulum and moving pendulum. Linearized moving pendulum I want at the end of the semester. So what we're gonna do, I'm gonna say I remove the sign, right, everybody? Because we linearized, and cosine is 1. Here we go. See? Here is x double dot over L, and here is theta, or M1. Everybody clear? Yes? Yes, everybody? And here you have to have, this is M3, because your new variable is M3 here. So here again, M3 is for pendulum angle, M4 is for angular velocity, and dm4 is for angular acceleration. Clear, everybody? Yes? What I did? Because this is your new angle, M3. This is for, let me connect this to this. Okay? Now, I have to change here also. Now we have 4 initial conditions. These 2 for the initial angle of the nonlinear pendulum, initial angular velocity of nonlinear pendulum. Now this is for initial angle of the linear pendulum, moving pendulum, and initial angular velocity of the linear pendulum. Clear? Yes? We got it? So I'm going to compare that. How? I'm going to say, hold on. MATLAB understand this. Means I have another plot. So I'm doing like this because I'm teaching you. Normally I don't do this, okay? I'm going to move it here and here and here. So third state variable for the linear pendulum. So it's going to be 3. I'm going to say R. Huh? Here we go. Let me run it. You see, there is a slight difference between the linear and nonlinear pendulum motion. And you tell me why, guys. Why there is very slight, almost negligible difference between the linear and nonlinear. I told you the answer in your notes. Go and look at it. And look at the scale of the angle of the moving pendulum, linear and nonlinear. Angles between what and what? You tell me. Which degree? Which degree? Guys? Yes. And look at your notes. I told you linearization for moving or stationary pendulum is valid between which angle? You have in your notes. Between 0 and 6 degrees. Remember? Yes? So that's why you are very close to that range, and that's why your linearization works well here. Okay, works well here. So I'm gonna add here, because you have to know that is legend of the first is nonlinear and the second is a linear moving pendulum that we want to control. Okay, and bam, and I'm gonna add this interpreter Oh, LaTeX. After graduation, you can use these codes because I'm gonna expand million codes with you, okay? Hold on, I want to make sure that I'm right. Yeah, okay. Always do this. Okay, and here you have to put, for the Greek letters, do like this. When you use this command, do like that. And let me see if it works. Yeah, see, it's so professional. See how it's writing? Even you can write more professional like this. Say theta power of circ. It gives you angle. This is command in MATLAB. When you are a control engineer, you have to know this. Yes, see? Theta degree. Do you see that, everyone? Yes? And the nonlinear moving pendulum, linear moving pendulum. Okay? So, these are, we plotted the angles. Now, what I'm gonna do, I'm gonna also plot the angular velocities. So for the first nonlinear is 2, and this is for 4 state variable. And I'm reviewing this multiplication because this is radian per second, right? So this is theta dot. So you can write like this, theta dot, exactly as it is. Do you see that? Theta dot. And it's gonna show like that. Here we go. Bear with me. Here we go. See, theta. Oh, I have to remove this, guys. Sorry. I have to remove this. See? See, this is the theta dot. Angular velocity for nonlinear is the blue one, and the linear one is the red one. See? And they overlap because the angle is between 0 and 6. Everybody following me? Yes? You got it? So, bear with me because I'm not done yet. When you graduate, I want that to be a good representative of the SDSU control class. We have another graph. We name it, I'm writing here to you, phase port rate. Means that you are plotting, the x-axis is the angle, and the y-axis is the angular velocity. In nonlinear control, you have to know it, but I'm giving you as a gift. So it's going to be 3, and here, no, 1 and 2 for the first, and 3 and 4 for the linear version. See? There we go. When you hear that, you have to know that you are in the domain of phase portrait. Phase portrait, okay? So here gonna be, here we go. Okay. Okay, let me plot it for you. Oh, yes, that is so sexy, guys. See, the phase portrait is angle versus theta dot. Position of the moving pendulum to angular velocity. You see? This is, we call it phase portrait, nonlinear control and the nonlinear dynamics. But I want to expose you. Okay, if you don't go to grad school, at least you know what it is. When you're working in a big companies like a Tesla or the NASA, when they are talking about, at least you know what it is. You got it? Yes, everybody? Huh? So, Guys, remember that, bear with me. Let me go back to the notes. I'm not done yet. I have lots of things to do. I said in the code that your disturbance, what happened? Okay. I said the disturbance, I said the x of t was sine of t, remember? Yes? Now I'm saying, you know what? X of t is 10 sine of t, our new disturbance. Amplitude is 10 times. So x double dot gonna be again 10 cosine of t, and x double dot, our disturbance, gonna be minus 10 sine of t. So you have to multiply by 10, right? You got it, everyone? Yes? I want to see the effect of that in the control that we're gonna go eventually. This is our disturbance of the system. There we go. Okay. So here you have to say disturbance is 10. Okay, you got it? Do we have another MATLAB is running? Oh, okay, good. Okay, I just increased the amplitude of the disturbance. Now let's see what we have. Oh, guys, look at here. You see big difference between the linear and nonlinear now. Yes? Yes, guys? Why? Because the range of the pendulum is beyond 6 degrees, between 0 and 80 degrees. So linearization is not valid anymore here. So we have to be careful because we are in the linear control systems. See what I'm saying? So when I say that you have to linearize nonlinear system around the equilibrium point, means around the equilibrium point. For pendulum problem is around between 0 and 6 degrees. For different systems, different numbers. See what I'm saying? Yes, you got it? So even that you go to angular velocity is a big difference between nonlinear and linear system. And obviously phase portrait is completely distinguished. Here we go. Do you see? Now they can distinguish between them. And if we increase the amplitude of the disturbance of the system based on the block diagram, I'm gonna put say 50 now this time. You're gonna see the difference between them and invalidating the linearized differential equation more and more. Okay? These are the things that you have to know as a fundamental. Oh, see? Do you see, guys? This is completely nonlinear is different with the linear. Linear remains the same profile. Did you notice that? But the nonlinear is absolutely crazy. And the reflector, see here? Oh, look at here, guys. Nonlinear is like this, huge number, and the linear stays marginally stable. But this is not marginally stable, it's going to be unstable. Look at the angle. How much is that? Read for me. Read for me. Minus 1200 degree. The system becomes unstable. See? But still, your linearized system is marginally stable, almost. It's oscillating forever. See what I'm saying? Everyone? Can you hear me? Yes? Guys? Hello? Yeah. Okay. So, now, after knowing that, the question is that where we have to control this. Eventually we have to control here. You have to say plus u of t. U, control command, must be here, that's right, plus u. Okay, and I'm gonna teach you how to design this u. We have to define u here. U is here in this class is PID controller. This is command I'm putting here, not exactly the same command. PID controller. And then we're gonna add the system that based on this use. Okay, you got it? That's everybody? Now, let me go back. I'm not done yet. Let me go back to the notes. I told you that if you remove the right-hand side, you have the stationary pendulum. Remember that we derived the homogeneous solution? So I want to see what's the effect of disturbance with not disturbed pendulum. Okay? So what I'm going to do is simple. Now you know the rule. Now you know the rule. I'm going to increase to 6, and I'm going to add this to linear pendulum without disturbance. There we go. Only 5, 6, and 6. There's no disturbance. Bye-bye to disturbance. And here gonna be 5 and linear pendulum. Here we go. And I'm gonna keep it to low disturbance. And here you have to add 2 initial conditions for 5 and 6. And then you have to add the line here. Plot, hold on. This is gonna be 5. And oh, actually this, hold on, grid, and here we go, and this is gonna be 6 angular velocity, and for the phase portrait this is gonna be 5 and 6. I'm gonna add here nonlinear. Now I'm gonna add this moving pendulum, moving linear pendulum, and here is stationary pendulum that we solved in differential equation. Here we go. I'm gonna add it here, and the moving, and also this is moving nonlinear, moving nonlinear, and I'm gonna copy paste and put it here. Here we go. Okay, now let's see what's the difference between them. First, let me check it everything. And I'm gonna make it to 20 seconds to visualize what I'm talking about. This is sine of the disturbance to the system. Here we go. Okay, before going here. Oh, what's that? Oh, this must be green. This must be green. And this must be green. What's wrong here? Oh! Yeah, everything's right, no? Yes. So 5, 6. Okay. Why it doesn't? Oh, oh my God, I'm stupid, guys. Sorry. This is no disturbance. I have to give some initial conditions. I'm starting from 45 degree. Look at here, guys. When I say I'm getting older. When I say this means that there is no disturbance to move it. So remember that I solved mathematically for you. So initial conditions is 45 degree, as I told you, and I'm gonna release from here. So we have to have initial conditions, okay, based on gravity. So where we are? Oh, okay. Now it must work. Sorry, guys. Okay, that's fine. Good. See the difference between the stationary linear pendulum, purely sine solution as we derived by our hand, and it's a marginally stable system because two roots or the poles is on the imaginary axis I explained in the previous class. But you see that for the linear moving pendulum is not completely sine, but it's a harmonic. Do you see that? That's the difference between them. So the disturbance here affect a lot on the system. Disturbance is that sine of t. You got it? Everybody? Yes? Huh? So I'm done now for now. I'm gonna send it to you, but maybe I back to this later because I'm gonna add more details on this in the next class. So as now we know how to go design a MATLAB code for the control class and then add the controller eventually through the semester. We're gonna back to this several times. Now I'm gonna tell you, you know what, guys? This is our moving pendulum. Continuing the lecture. Here we go. Don't worry, I'm gonna send the M file by the email to you. Okay. And now look at here, guys. This was our block diagram. Desirable error signal, controller being added with disturbance. Then goes to the moving pendulum internal dynamics G. This gives you the real angle. You know what? I'm gonna add now one more detail because I'm gonna teach you step by step. Here, I told you you have a sensor here. Remember, guys? You have a sensor H that measuring that. In addition to disturbance, the control system, sometimes you have measurement noise because this sensor, okay, sensing the real output, but in most cases, you may have we are showing with N in control, measurement noise, measurement noise. Here we go. So not only you have to, in the control systems, this is feedback. Again, guys, when you see this, let me change the color. This negatives means feedback. Positive means feed forward. Okay? So this is unity, this is feedback. Okay? Feedback. Again, feedback. In the code that I presented, I'm going to teach you how to add this controller to the code. Okay? So I'm gonna add a fourth mission of the control. In addition to rejecting disturbance, we have to be able to remove noise, from system. Which noise? You tell me. Measurement noise. How? By designing this controller. I'm gonna teach you step by step. So you have disturbance to the system, you have measurement noise to the system. Now you have to design a controller to reject both, eliminate noise and reject the disturbance to the system. So if this is the disturbance, as we know, when we have a, I don't know, whatever sensor you have that measure this angle, maybe you have some dust in the air, maybe this is just the laser measurement system, the dust effect on the measurement. So you have to design a controller that keep, for example, I told you, the angle of this as 45 degrees. This is desirable, okay? While you have, means keep it forever. As you saw in the MATLAB code, as it oscillates, but I want to keep it at 45 degrees. While you have disturbance and while you have noise. You got it? Yes, everybody? Huh? Yes? You got it? Hello?
Yep.
Good. So, guys, everything is math. Everything is math. Now we arrive to the domain of the linearized. Now you know why we did it. What's the difference between linear and nonlinear? How we can linearize? What's the equilibrium point? Linearization is only valid around the equilibrium points. If you are far from the equilibrium points of any system, not pendulum, temperature, room, pressure of the tank, angle of the robot, I don't know, trajectory of this Falcon 9 that Elon Musk sent to the international station, whatever. Okay, if you're far from that and you're not linearized, you have to expect a large difference between the responses. And what you design as a controller sucks. I'm going to show you in math and in code. Okay, and this is minus x double dot. Now we're on the linear domain. Forget about the nonlinear. Okay, guys, you know what? I want to be crazy for a second. And I say disturbance to the base of this pendulum is this value. Any of you know what is this? What is this? Do you know what is this?
Yeah.
Yes, impulse. The gentleman, you said, what's the definition of the impulse? You tell me in the lay language, not in technical language. What's impulse? So I'm exactly sure. I'm sure that you are looking at the boxing. That's right. Any impact by the boxer is the impulse. very huge amount of force in very, very short amount of time. That's the impulse. Like I'm hitting the table. See, that's impulse. Huge amount of force and in a very short period of time. So if I want to translate it to 5 years old, your sister or brother, that they have nothing with control, so delta of t or impulse in mathematics, you can say this. After zero is nothing. At zero, you have a huge force, and then vanishes that huge force. And after this, again is zero. This is impulse. You got it? But if I want to define it impulse, one of the inputs in the control system that we're going to deal for the at least 2 or 3 weeks from now is its mathematical definition is this. At time equal to zero, how much is value? You tell me. At time zero, here is zero. How much is the value of this? Give me a number. Infinite means unknown. Unknown. This is mathematical definition of impulse. When t is not zero, how much is that? Zero. Now, I said base the impulse I'm applying to the pendulum is impulse. You're gonna tell me, Payman, are you stupid? No, I am not. The rover on the Mars that's working right now, we have no access on that. And sometimes maybe there is a 1 degree of freedom robot manipulator that taking the soul from the Mars, putting on the rover, because of some rock, the base movement of that means the rover is subject to impulse. See? Okay. Can we measure it on the Mars? No. Huge impulse. We don't know. Okay. So I have to find the x dot and x double dot. So guys, I'm asking you, what is x dot from here? What's the definition of that? At time zero, unknown. What is time derivative of unknown? Unknown dot? Sucks. We don't have it. What is the x double dot of sucks? Probably sucks double dot. If you put here sucks double dot, you cannot solve this equation anymore. You get it? Yes? Understand? So that's why we are in this course living time domain and arriving to frequency domain. Through what? Through Laplace transform. We are living time to frequency omega radian per second, because we cannot solve a simple differential equation by impulse. Or later I'm going to show today by step. Or later I'm going to show you by ramp. Okay, input. So we have 4 important inputs to the system. For any system we have to deal with impulse, as I showed you, is delta of t. Definition is unknown when time is 0 and 0 when time is not 0. 2, let me change the color, step function. And the unit step that we're going to focus here in this class, we are showing unit, this kind of 1 of t, and we are plotting like this, and I'm pretty sure you have seen that. Here we go. Unit step, here is 1. and here's constant 1. Here we go. Unit step. Before 0 is 0. Before 0 and smaller than 0. And after greater than 0 is 1. Is a discontinuous function. Okay? So I can say time derivative of, I want to examine your basic knowledge of mathematics. What is time derivative of unit step? What in high school, what's the meaning of the time derivative? Means slope at here, that's right? Slope of here. What is slope at here? Time derivative, respect to time. Obviously is infinity. Or what? You tell me. Unknown. Or is delta of t. So if x of t to the base of the pendulum is unit of step, as a disturbance, x dot gonna be delta of t. X double dot gonna be sucks. Again, you cannot solve it. See? Intentionally, I selected this example to make you a solid foundation of why we are going to Laplace transform to frequency domain. 3 that we're going to deal in this course. Ramp input. Ramp input. I bet you have seen this in your middle school, not in the high school. Time means your x of t is time. See, this disturbance here, I mean, these are inputs to the system, but I'm saying that for sake of disturbance, I'm saying x of t. Okay, this is a, here we go, ramp, t versus t. So x of t, x dot gonna be unit step, say. X double dot that gonna be how much? How much? Impulse. Again, I cannot solve it as a disturbance. Fourth that we're gonna consider in this course is parabolic input to the system. Parabolic means your input to the system is 1 over t squared. Okay? Even if you select this, your x double dot becomes unit step, a discontinuous function. Okay? So these 4 steps input to the system forces us that we go from time to frequency domain. You got it? And I'm going to continue the next class from here, except that let me introduce to you our Laplace transform. What is, we are showing with L, Laplace of a function of time is, this is how we show Laplace, f of capital S, time to frequency. S is a variable in frequency domain, is j omega, is a pure imaginary number. Okay, omega has a name, is characteristic frequency. So what is Laplace based on mathematics? Is integration from 0 to infinity exponential of minus st, the function that you want to find it, dt. And we're going to work on this in next class and do the MATLAB also. You got it, everyone? Yes? Understand? So we are moving from, where is that? We are moving from the time differential equation to transfer function of frequency domain. And it's very easy for control systems of undergraduate. Even if you go to grad school or PhD, if you go to NASA, you can linearize systems without the current point and go to frequency domain. You're going to learn a lot by coding and Simulink. I just did in the coding of MATLAB, but I'm going to teach you also the Simulink, okay? You got it, everybody? Yes?